if we were to take two solutions of a 0.2 molar copper solution and a 0.05 molar copper solution and put them in the same beaker, the concentration of this 0.05 molar would increase, this 0.2 would decrease, and they would meet somewhere in the middle, and they would make one solution. If we separate them in a galvanic cell, and we make a battery out of them, we can get a solution, we can get the molarities to meet in the middle the same way just by transferring electrons. So we can get the same effect. So what happens is if we've got, let's call this one our 0.5 molar solution. Okay, so 0.5 molar copper 2. And then this side we will have the 0.2 molar. Okay, I need to erase that. This is not 0.5, 0.05. So these molarities are going to change, and there's going to be an electron flow between them. Now, these molarities are going to meet somewhere in the middle, and that's our really clue to our half reaction. We need the concentration of this copper to go up and this copper to go down. That tells me the half reaction. So assuming we've got copper electrodes on each side, we've got solid copper available. In order to get this copper to go up, we need the solid copper to turn into copper 2. And in order for this copper to go down, we need the solid, or the aqueous copper 2 to turn into solid copper. So those are our half reactions. This one is going to have 2 electrons as a reactant, and that's going to make this my oxidation side and my anode. And this one will have the 2 electrons as a reactant. Let me sneak in here to write it a little tighter. And that's going to be my cathode. So this is a reduction. In order to figure out the electron flow, the electrons are going to go this way, off of the anode and onto the cathode, as they always do. So we can get the direction of the electron flow, and we can designate which side is the anode and which side is the cathode. The goal of this concentration cell, it's a proof of concept. Even though they're both copper, if their molarities are not equal, 0.05 and 0.2, their molarities can still equalize even though they're separated just by flowing electrons. I can get more copper 2 in this side if I lose electrons, and the copper becomes copper 2, and I can get a smaller molarity on this side by gaining electrons and reducing these copper 2 aqueuses and depositing them onto this copper electrode. So here's another concentration cell with silver. If we had 1 molar silver and connected that on the other side with a beaker that was 2 molar silver, what would happen? Which one's the anode, cathode, and electron flow? Again, we need a higher molarity in this cell and a lower molarity in this cell so that we can get a homogeneous mixture. In order to get a higher molarity in my left cell, the way that I've written it, it's arbitrary, but I put it on the left, I would need solid silver. That's not it, solid silver. Okay, solid silver turning into aqueous silver. And that would cause an electron. So here again we found the anode. This handwriting is not working today. And then on the right side we would have, we need a lower molarity, so we're going to need those silver ions to turn into solid silver. There we go. Got the handwriting working a little bit better. And that's going to make this our cathode. The electron flow comes off of the anode and goes to the cathode, so it's going to go this way. Now, what would happen to the voltage in the cell direction if we were to replace the 2 molar with a 0.5? So if I lowered this molarity of the 2 molar silver to a 0.5, the electron flow would go the other way, because now it would come off of the 0.5 would be lower than the 1, and it would have to increase in molarity. So everything would be reversed and backwards. This galvanic cell has a copper and zinc solutions with 1.76 volts. And that voltage measures both of these at a 1.0 molarity. So this is my standard molarity, 1.0 molarity. And we can talk about Lechatlier in this scenario and say, okay, what happens if we changed the molarity? Lechatlier, we need to be very careful, works only when we are at equilibrium and then we shift away. We say, what happens to the voltage? We will look at other scenarios where these are not 1 molar, and we'll talk about how does that affect the voltage, but it's not Lechatlier because we're not at equilibrium and then moving away from it. It's just a different set of conditions. So if we were to add copper sulfate to the container with the copper electrode, that is another source of copper ions. Okay, so some of that would dissociate the copper sulfate, and that would be an increase in copper ions. And that would shift right, and we would expect that to increase the voltage. Likewise, if we added zinc chloride, that would be a way to increase zinc ions, which is a product, and that would shift left, and shifting left is going to decrease our voltage. So we can use Lechatlier under a very specific circumstance to see if molarities or voltages will increase or decrease once we're at equilibrium and start moving away from it.